or incorrect form for problem 1 should be. So I think that most of you understood negative refraction, that if you have a double negative material like mu epsilon here, a minus mu minus epsilon here, when the ray comes in, then the k vectors should be like this to do phase matching and energy conservation. Two key things are phase matching and energy conservation in order to match boundary conditions at the surface. I think most of you got that right. And then regarding the case of evanescent wave amplification, I think you will find that if you have R12 is equal to say mu2 k1z minus mu1 k2z over mu2 k1z plus mu1 k2z, and then you have T13 generalizes T12 K23 e to the I K2ZZ H has been the thickness of the slat minus 1 over R21 R23 e to the 2I K2Z H. I can hand out the solution after the lecture today. I actually may have written up the solution, okay, but let me hand that out after class today. What happens is that there are two scenarios. If mu2 equals mu1, or mu2 equals negative mu1, okay, then in this scenario, which is a propagating spectrum, K2z should be the negative of K1z. Okay, K2z. So then the difference in sign cancel, and then what happens is that this is 0 for propagating spectrum. Okay, this is 0 for propagating spectrum, and for propagating spectrum, K2z equals minus K1z for matching, for perfect matching. That should be the scenario for this case. And then if you look at this, Tij is 1 plus Rij. And then because this is 0, so Tij is just equal to 1 for perfect matching. Okay? So T13 equals 1, but with this phase, this is 1, then you have this minus I K1Z. H kind of phase regression for the propagating spectrum. So everything is fine and dainty because there's a phase regression going on here. But then there's only one scenario that works actually. You actually have to pick this one. You can pick K2z equal to plus K1z. That gives rise to infinity over here. You still get the same answer at the end, okay, but that is not the right way to say. It should be that this should be the choice, that R12 go to 0, and then for evanescent spectrum, what happens is that you take the scenario of just one interface alone, okay, just one interface alone, and if there's an evanescent wave that is generated by the source, the evanescent wave will decay in this manner. If the reflected evanescent wave, they will decay in this manner away from the interface. There will be transmitted evanescent wave. Okay, the transmitted evanescent wave has to decay in this manner. So the excited wave at the surface has a profile that looks like that, where the wave decays exponentially away from away from the interface. If you have picked the wrong sign, then you will have exponential decay. So if I have perfect matching case, I have K1z equal to I alpha 1, say, K2z should be I alpha 1 for perfect matching. Okay, this should be the choice. Otherwise, you will have no exponential decay. So in this case, for the Evanescent spectrum, the choice should be actually K1Z equal to K2Z. Otherwise, it becomes unphysical. If you pick, as some of you say, K1Z equals minus K2Z for this case, you have an exponentially growing wave in this direction. You have an exponentially growing wave. If you have an exponentially decaying wave in this direction, you will have an exponentially growing wave, and that's not physical. Okay? So the choice here should be this one. And then in that case, you can see that R12, if this is a negative of that, if this is equal to that, then it's the denominator that goes to 0 now. Okay, so R12 tends to infinity. If R12 tends to infinity, you will see that this T13 tilde would tend to, this is dominated by Rij now, R12, R23, which tends to infinity, which is much, much bigger than 1. Okay? And then this one tends to infinity, so I can drop the 1 over there. So it's R12, R23, e to the 2i k2zh. These are very large numbers. They cancel each other. So the final answer is that it's minus 2i k2zh. But you have picked k2z to be I alpha 1. Okay, this gives rise to an exponentially growing wave. Okay, that should be the correct physical explanation. Don't, as many of you did, pick in both cases that K1z is equal to minus K2z. That's wrong for the Evanescent spectrum. It becomes an unphysical wave. Okay? Then you have this. Then the question is, what is causing the amplification of the Evanescent spectrum then? It becomes very puzzling because you have a mode excited at one interface, and then you have another mode excited at the other interface, but the wave finally ends up growing in the double negative slab. What happens is that you can think of a scenario like this, that there is some loss. Okay, if there's some loss, then there will be a surface +1 mode excited at one interface. And then there will be this exponential decay will excite another surface +1 mode. The reflected one will be also exponentially decaying. And the two surface +1 mode will look something like this. Okay? But it turns out that in the perfect matching lossless case, the scenario that this evolves to is that you need only a very small amplitude in the first interface, infinitesimally small amplitude, okay, to excite an infinitely large amplitude on the second interface. Okay, just a tiny amount of surface +1 mode on the first interface is good enough to excite the surface +1 mode on the second interface. This is called resonance tunneling. Okay, the wave is actually evanescent through the slab, but it has enough energy to reach to the other end, excite the other surface +1 mode. And since there's no loss, in principle, that surface +1 mode can grow to an infinite amplitude. So actually, there's no violation of physics here. It takes a surface +1 mode from one interface to excite the first surface +1 mode in another interface. So if you look in here, you see an exponentially growing wave. In the limit of no loss, this just looks like this. The wave just grows. The wave just grows exponentially. Or maybe just grows exponentially. And it's that the thing is amplified. So the amplification is due to surface +1 mode-like condition, and then it's due to resonance tunneling. Okay. I think none of you got this right. That's fine. This is the correct way to explain the physics correctly. Second problem. Well, I'm glad that all of you got it right. Most of you, because it's written up in Jackson, it's written up in Stratton, it's written up in Harrington. So it's a textbook research problem. So you know how to do that right. Third problem, I think most of you get it right. It's written up in the paper, just fill in the blanks. Okay. Get it. Fourth problem is just a simple exercise in Hilbert transform. I just want you to understand that the Hilbert transform of sine is minus the cosine. So if you have a sine function that looks something like this, the Hilbert transform it will look like a minus cosine, so it will look something like this. Hilbert transforms to cosine omega tau. And then if you have something that looks like this, if you Hilbert transform to something like this, I suppose. Okay. So you can look at experimental data. You can eyeball experimental data. And you can do the Fourier transform in your head. That if I do some measurements, and then there's a resonance condition, and then if I have one thing that looks like that, okay, the real part of the transfer function looks something like that. The imaginary part must look something like that, roughly. Because they're the Hilbert transform of each other, you can Fourier analyze this, break it down into summations of cosines. Do the Fourier transform or the Hilbert transform in your head. All the cosines becomes sine. So if you look like this. So in the lab, you often observe this kind of behavior. And if they don't obey this kind of behavior, your measurement data must be wrong. Okay, you can do the transformation in your head. Fourier analysis, do the shift to cosine from cosine to sine, and then you get this, and vice versa. Okay, they should be related as such. There's one thing that I want you to learn from Hilbert transforms. Any other questions? Yes?
Do they actually measure both the real and the imaginary part?
In the lab, you could. Right, for instance, this could be R. This could be JX in the lab. This could be Z, a measurement of Z omega. R plus JX omega. This is a transfer function between current and voltage in a linear system. So these two must be Hilbert transforms of each other. Okay? And you can measure epsilon, you can measure many things. Many things are causal. Think of it as correspond to a causal function in the time domain. Then the real and the imaginary part must be related to each other by Hilbert transform. Okay. A lot of the things we measure in the lab will look something like this. Okay? As long as they represent a causal quantity. Okay? Any other questions? Okay, if not, then we move on to a new topic. Okay. We talked about discrete electromagnetic theory and how useful it has been. It has been used a lot by people, even outside engineering. People in the physics community are using FDTD algorithm to get solutions because the algorithms are so useful and they can be readily written to solve many problems. But FDTD, or the E algorithm, okay, allows you to solve a problem in a finite domain. So if you have a finite domain, you can solve this problem very easily. You can solve Maxwell's equations. But oftentimes we like to do simulations in an infinite domain. And we also like to do experiments in an infinite domain. In the lab, what we do is to use what is called an anechoic chamber. Okay? Anechoic chamber. And what you do then is to put absorbers on the wall. I think Kurt of Malawi can take you for a tour of upstairs. There's one big one upstairs. You take a look at it, you can see that the wall has all this cone-shaped thing. It's not microwave. So when microwave hits this absorbers on the wall, they don't bounce back. I believe the word anechoic came from acoustics. Such a kind of chamber was first designed for acoustics. And echo means no echo. Okay, no echo. This is what it means. Okay, so no echo chamber. And you can have such a kind of chamber too in acoustics. In acoustics, it's more drastic. I had walked into one before. But if you talk in this room, we hear echoes. Okay? But if you walk into an anechoic acoustic chamber, you hear a big silence. There's nothing. When you talk, the voice doesn't bounce back from the wall. So it is as if you're talking in an infinite space. The voice doesn't come. It has to give you a very different feeling. So how do we do this kind of thing in the numerical world? So in the numerical world, we use what is called the absorbing boundary condition. And there have been many, many absorbing boundary conditions that have been defined to absorb the wave. But one of the most powerful ones is the recent one proposed by Barringer called the perfectly matched layer. Okay, proposed by Jean Pierre. Probably spelled this way, Jean Pierre. Barringer. So he's French, so we call him Barringer instead of Barringer. You see, we call Schlumberger instead of Schlumberger. Okay, because Schlumberger is a French company. So, but then I later found a way of describing this using a very succinct method called stretch coordinate. PML. So I will describe this work then. It was written up first in a paper by myself and Whedon. Okay, and I'll describe this work today as to how we can use stretch coordinate concept to design a perfectly matched layer. And the perfectly matched layer can be used as an absorbing boundary condition for a finite difference time domain simulation. Okay, let's see. So to do this stretch coordinate PML, we first have to actually modify Maxwell's equations. So I'll talk about modified Maxwell's equations first. So we propose to modify the del operators we have in Maxwell's equations so that Maxwell's equations becomes something of this form. Curl of E is equal to I omega mu H. And then curl of H is equal to minus I omega epsilon E. And we modify this del operator depending on if they're operating on the E field or the H field. And then you will have, because if you take the divergence of this equation, okay, you get this equation. So we have divergence E dot mu H must be equal to 0. Okay, we can put a J here if we wish to. And then we have divergence of H dot epsilon E is equal to charge. Okay, so these are the modified Maxwell's equations. And we'll do coordinate stretching. to modify this del operator.
How do we know where to use E and H?
What is that?
How do we know where?
Okay, I'll talk about it later. Okay, I make it very general so that you can modify the del operator. And I will do coordinate stretching in the sense that if I have a wall where I describe this wall with one coordinate system, okay, but everything I have to observe is very, very small. Okay, everything I have to observe is very, very small. Maybe just around the origin. So it's kind of wasteful to describe the wall with a coordinate system measured, say, in terms of meters. Say if you live in a world where everything is measured in terms of meters. Okay, it would be very clumsy to use this meter system to observe the denominator wall, which is 10 to the minus 9 times smaller. Okay, so we define a coordinate system. We redefine our coordinate system so everything is measured in terms of nanometers. And in this new dimension, new unit that we use to measure distance, then everything on the order of nanometer has a unit of 1 in size and length. So coordinate stretching is very similar in the sense that you change your unit so that z becomes like let me see what notation I use, like ex, ez, z, y becomes e, y, and then z, x becomes e, x. So you change your variable so that if this thing is in terms of, in the unit of meters, okay, this is in the meter, in the unit of nanometers, okay. So you need to multiply this by a very small number, for instance, in order to get this to match, okay. So coordinate stretching is something similar to that. So I would define my thing with this. So partial z will become 1 over ez partial z after I do coordinate stretching. And then partial x will become 1 over ex partial x, and then partial y will become 1 over ey partial y. Okay? So then I would have DRE becomes something like 1 over ex partial x plus y, 1 over ey partial y plus z, 1 over ez partial z. Okay, this is how I modify the del operator by coordinate stretching. I allow the stretching to occur with different values in 3 different directions. And I can also define a similar stretching operator for the magnetic field. I will call that hx partial x y, 1 over hy partial z, 1 over hz partial z. Okay. And let me see what kind of plane wave solution do I get when I do this coordinate stretching. If Maxwell's equations still emit plane wave solutions, so let me assume that E is of the form of the plane wave solution. Okay, E field is something of this form, and then H field is something of this form as well. Okay, and it turns out that even if I stretch the coordinate system this way, plane wave solution still exists, and I would have K, as is usually the case, is a K vector with 3 components. Okay, K in this case is just a vector with 3 components, and then if I substitute this in and replace partial x with ikx partial y with iky partial z with ikz due to the usual thing, then the modified Maxwell's equations becomes something like this. Okay, the first one becomes something like this, which is something you did for your take-home exam as well. Okay, but without coordinate stretching. KH cross H minus omega epsilon E. Okay? Where KE is defined to be this vector with partial x replaced with KX. Okay, so KE is actually equal to x 1 over EX KX plus y 1 over EY KY plus Z 1 over EC KZ. And then do the similar thing for KH. KH is just x 1 over HX KX plus y 1 over HY KY plus Z 1 over HZ KZ. Okay. So this is what modified Maxwell's equations become in the coordinate stretching form. And I can do the same manipulations that I used to do for Maxwell's equation. I can multiply this first equation by KH cross. I cross the first equation, and then on the right hand side I will have KH cross H, and then I can replace KH cross H with this. And I will obtain an equation for, let me see, if I do that, I will have that. Or I can also pick to multiply the second equation by KE cross. Okay, I will get an equation that looks something like this. Very similar to what I would have gotten for the unstretched case. KE cross KH cross H. Okay, KE cross. I multiply the equation by that, and then after replace K cross E with that, I get this equation over here. And I can use the back of the cat formula for this, which says that A cross B cross C is equal to the back of the cat B A dot C minus C A dot B, back to the cat formula. And if I do that, then I would have this in equal to, this would be my B, KH, KE dot H minus KE dot KH dot C, C would be my H. Okay. Many of you use this formula to prove why E cross H is orthogonal to K in the first problem in the take-home exam. It's a nice proof. Okay. So we have this relationship, but KE dot H must be 0. KE dot H must be 0 for a homogeneous medium. Okay, from this equation, I can prove that KE dot H is equal to 0 for homogeneous medium. Okay, so I have this simple relationship that omega squared mu epsilon must be equal to KE dot with KH. Okay, so in this modified Maxwell's equations, I have these two dotted together, and this must form this dispersion relationship, and then I can define a kappa square. I define this to be kappa square, which is equal to 1 over ex hx kx squared plus 1 over ey hy ky squared plus 1 over ez hz kz squared. Okay, I just got these two things together, I get that. And in order to solve this equation, I can do a very simple assumption that kx is equal to kappa. Okay, this is kappa squared. I assume that this is kappa ex hx sine theta cosine phi. Kx equals that, and then ky is equal to kappa Ey hy sine theta sine phi. Okay, and then kz is equal to kappa Ez hz cosine theta. Okay, so if I make these three assumptions, then these values of kx, ky, kz solve this equation immediately, or satisfies this dispersion relationship. It's a very simple observation. So the special thing about it, so far everything is exact, so far everything is very mathematical, and the stretching parameter EI and HI can be anything. I say it's something that changed from one scale to another scale. This is called coordinate stretching. But it can also be complex. There's nothing that stops it from being complex. So EI, HI can be anything, any number, any scalar number. And they can even be complex numbers.
Excuse me, about EI and HI.
Yes.
Because the electric field can induce magnetic fields and
Okay.
vice versa, right?
Mm-hmm.
So should it be required that EI equals to HI? For example, EX and HX should be the same. Otherwise, we cannot find the corresponding electric or magnetic fields.
Yeah, it turns out you're quite correct. It turns out that finally, after you go through the analysis, EX and HX are equal. EY and HY are also equal. Okay, and so they are actually equal to each other. But from this point, at this point, up to this point, we have not assumed them to be equal. It can be any numbers now, and everything is still valid up to this point. Okay. So if we assume that they are equal, then something interesting happens. Something interesting happens in the sense that then what we have then is that kappa Ke is equal to Kh. And this dispersion relationship becomes something also simple. Okay? Something also simpler, and then you just have kappa E dot kappa E, no, sorry, not kappa E, Ke dot Ke is equal to Kh dot Kh is equal to kappa squared. Okay, if they're equal, then this equation just becomes that, and this is equal to omega squared mu epsilon. Okay? But another thing that is quite interesting that happens is that if you look at this equation, say if I just look at this equation, I can multiply by, or dot multiply by Ke cross E dot with Ke cross E. But Ke cross E is just omega mu H. So if I multiply the left hand side by this, I can also multiply the right hand side by that. H dot H. Okay. I just derive this equation from here. Multiply again 2 times, I get this equation. And I use the fact that this can be rewritten using this cyclic rule. A dot B cross C is equal to C dot A cross B is equal to B dot C cross A. This is a cyclic rule for cross and dot product. I can rewrite this as KE cross KE cross E dot E. I just use this cyclic rule and then move one of the KE in front and then dot with the E at the end. Yes?
Shouldn't that be omega squared, u squared, e star h?
Let me check. I multiply by the KE cross E, and then I multiply by the same thing on the right hand side. Mu squared. Yeah, mu squared. Yes, correct. Mu squared. Okay. H dot H. So I rearrange the left hand side so that it appears to be something like this. But then this can be rewritten using the back of the cat formula as KE dot KE E it can be rewritten like this, but with the K dot E term disappearing. The other term disappears because K is orthogonal to E. So this can be rewritten like this, and then this dot with E is equal to omega squared used by H dot